Hello, folks. We're going to go through some more homework for the Engel and Reid Physical Chemistry textbook. Going through Chapter 9, Ideal and Real Solutions. We'll start with problem 2. Go to 4, 7, 16, 25, and 33. Starting with problem 2. At a given temperature, a non-ideal solution of a volatile components A and B has a vapor pressure of 795 torr. For the solution, the Y of A, so the gas phase mole fraction of A is 0.375. In addition, the liquid mole fraction of A is 0.310. Given that the P star of A is 610 torr and the P star of B is 495 torr, calculate the relative activity and activity coefficients of A and B. Okay, for this one, we need these two facts. That activity is given by the actual pressure over the ideal pure pressure of a gas. So pressure of A over its pure pressure. And the activity coefficient is given as the activity divided by the mole fraction of A. So we're going to be able to do that given that factor. So with that in mind, we know that the Y of a given compound is going to be the pressure of that compound over the pressure total, and that the Y of A plus Y of B must equal 1, and the X of A and X of B must equal 1. So we know that Y of A is equal to 0.375, and X of A is equal to 0.310. So Y of B must equal 1 minus 0.375, which gives us a Y of B of 0.625. And X of B would be 1 minus 0.310. And so that would be X of B must be 0.690. That's a good starting point. Now, this in mind, we need to find what are our individual pressure components to find out what is the activity. So, if I want to find the pressure of A, it's going to be our Y of A times our P total. So 0.375 times the total pressure of 795 that we were given at the beginning. If we multiply that out, we would have 298.125 torr. I'm taking that out far too many places, but that's good enough. It's good for now. And the pressure of B is going to be the Y of B times our P total. So that's going to be our 0.625 times 795 torr. Once again, pulling that out, we'd have 596.875 torr. So now we have, this is our pressure of A, this is our pressure of B. The next step is just to find the activity of A. The activity of A is just going to be the 298.125 over the P star, which was given as 610 torr. 610 torr. And you get the activity as 0.4887. Let's go ahead and get the activity coefficient while we're here. The coefficient would be our 0.4887 divided by our mole fraction in the liquid phase, so 0.310, and you'd get a activity coefficient of 1.577. Let's continue along for B. The activity of B is going to be something like 496.875 divided by its P star. I think we said that P star was 495. So the activity of B is actually 10038. And so the activity coefficient of B, 10038 divided by its mole fraction of 0.690 would give us activity of B as 1.455. And that would be our values, 1.455, 1.577, and our activities of 0.4887, 4887, and 10038. Normally, we might have to use the K sub H, the K of, to find this value, but given the fact we don't know A, we can't really find that. We don't really know what A is. That's the best we can do. Okay, problem 4. At 350 Kelvin, pure toluene and hexane have vapor pressures of 3.57 times 10 to the 4th pascals and 1.30 times 10 to the 5th pascals, respectively. Calculate the mole fraction of hexane in the liquid mixture that boils at 350 Kelvin at a pressure of 1 atmosphere. And for A and B, calculate the mole fraction of hexane in the vapor that is in the equilibrium with the liquid of part A. Okay, for this one, there's only 2 factors we really need. P hexane pure, which is, as we stated, 3.57 times 10 to the 4th pascals, and P pure of toluene. Sorry, that's toluene right there. That's hexane. 1.30 times 10 to the 5th pascals. And you need one other fact, that when a solution is boiling, the vapor pressure is equal to the atmospheric pressure. So 1 atmosphere, or 101,325 pascals, is going to be the P total for a given pressure. So with that in mind, we have an equation that says the P total must be equal to the P2 star plus P1 star minus P2 star times mole fraction 1. So with that in mind, if I call that one P1 and X1 and that P2, I can easily solve this equation. These are just constants, and I'm just solving for X1. So 101,325 is equal to 35700 plus 130,000 minus 35700 x1. Doing some quick calculations. Getting this to the other side. In this to the other side, you would have 101,325 minus 35700. You have 65625 equals the difference there, 130,000 minus 35700, 94300 X of hexane. And you could do it either way, as long as you remember what mole fraction you're solving for. So 65625 divided by 94300, it gives you a mole fraction of hexane, X of hexane, to be something like 0.6959. So we'll just say 696. 696 as our mole fraction of hexane. So that is our answer of A. Our answer for B uses the other equation, that Y1 equals P1 star P total minus P1 star P2 star over P total minus P1 star minus P2 star. With that in mind, we already know that solution. We've already done that. But plugging our numbers in, we have 130,000 times 101,325 minus 130,000 times 35700 divided by the 101,325, and then 130,000 minus the 35700. So let's solve that. 101,325 minus 35700 is this minus this is 65625. We already found that. And we multiply that by 130,000. So on top I have 853,125, two zeros followed by two more zeros. Big number. That's fine. On bottom, we already know this. That's the 94300. 300 times 101,325. 9,554. 947. 500. Those two numbers divided by each other gives you the mole fraction of hexane to be 0.8928, around to 893. So hexane is in greater proportion both in the liquid and in the gas phase. But that is fine. That is our solution to number 4. Moving right along to number 7. The osmotic pressure of an unknown substance is measured at 298 Kelvin. Determine the molecular weight of the concentration of the substance. If the concentration of this substance is 31.2 kilograms per meter cubed And the osmotic pressure is 5.30 times 10 to the 4th pascals. The density of the solution is 997 kilograms per meter cubed. For this one, it's a standard osmotic pressure one, but we have to work in reverse. That osmotic pressure is equal to RTC of our solute. Now, given the osmotic pressure is 5.30 times 10 to the 4th pascals, we need to convert that into atmosphere. So start that with 101,325 is 1 atmosphere. That number is 101,325. Something like osmotic pressure 0.523. I'll say 07 ATM. So 52307 ATM equals R, which is 0.08206 ATM liters mole Kelvin. And it's at 298 Kelvin. And so we can find our concentration. So 0.52307 divided by R divided by temperature gives us a concentration of something like 0.021, we'll say 39 moles over liters. Pretty standard so far. Here's where we get a little weird. So with that in mind, we're trying to find the molar mass of the solute. So the idea is that mass divided by molar mass is equal to moles, and molarity is moles divided by volume. Well, we're not really given a volume of solution, but we are given a concentration we're given a concentration in grams per volume. Unfortunately, we're given that concentration in grams per meter cubed, so we need to convert our liters into meters cubed. So times 1,000 liters per meter cubed gives you, we have 21.39 moles per meter cubed. So with that in mind, if I want grams per mole, I'm going to want, I need to divide the concentration in kilograms per mole, kilograms per meter cubed by this, in moles per meter cubed. So we can just go 31,200 grams. It's because it's 31.2 kilograms per meter cubed, and I'm going to divide that by 21.39 moles per meter cubed. We don't actually need the density of solution because we're not trying to calculate molality. If we were trying to calculate molality, maybe. But we don't actually need that in this case. With that in mind, you get something like 1458.6 grams per mole. Something like that. Problem number 16. Calculate the solubility of H2S in 1 liter of water if its pressure above solution is 2.75 pascals. The density of water at this temperature is 997 kilograms per meter cubed. Okay, to do this one, you need the equation that the pressure directly relates to the mole fraction times the K sub H of the solvent. So if we look at in water, the K sub H of water for this is 568 bar. And of course, 1 bar is equal to 10 to the 5th pascals. So with that in mind, the pressure of H2S, which is 2.75 pascals, is equal to the mole fraction of H2S times 568 bar times 10 to the 5th pascals per bar. And this will give us, what is the mole fraction of H2S? We do that, 2.75 divided by 568 divided by 10 to the 5th. And you get essentially X of H2S, the mole fraction is 4.84 times 10 to the negative 8th. The next step is to find out what is the molarity of this. To do this, we have to convert mole fraction into moles, which is a little bit of a tedious process. The mole fraction is moles of H2S over moles total, 2S, plus moles of water. So what we're going to do is say, we're going to make some assumptions about the moles of water, that moles of water are going to be equal to we're going to say 1 mole of water, and then base everything accordingly. 1 mole of water is 18 grams. 1 gram, or there are 1,000 grams, is 1 kilogram. And the density of water is 997 kilograms per meter cubed. And that's going to be 10 to the negative 3rd meter cubed is equal to 1 liter. So this is going to give us essentially our volume of water. We're going to make the assumption of 1 mole of water. So we're going to assume 1 liter of water. So this will get us the moles of water in 1 liter. So 10 to the negative 3rd times 997 times 10 to the positive 3rd divided by 18 gives us 55.39. So 1 liter of water has 55.39 moles. Well, now we have N over N plus 55.39 is equal to 4.84 times 10 to the negative 8th. In this case, we're just going to get that to the other side and evaluate. So we get that N equals 4.84 times 10 to the negative 8th N plus 2.682 times 10 to the negative 6. And if you solve for N, so get that to the other side, solve for N, you have N, the moles in 1 liter of water is 2.682 times 10 to the negative 6th moles in 1 liter of water. We're going to assume this is so small that it does not change the volume. And that's how we would do number 16. Number 25. A solution is prepared by dissolving 45.2 grams of a non-volatile solute in 119 grams of water. The vapor pressure above the solution is 22.51 torr. The vapor pressure of pure water is 23.76 torr at this temperature. What must the molecular weight of the solute be? Very similar problem here. So this one we're using P equals X times P star. In this case, X is X of water. So knowing the fact that P star is 23.76 and P, as we said, is 22.51. We can get that, dividing that, X of water is 0.9474. Okay, there's our X. Well, we can set now the, figure out how many moles must this be. So we have 119 grams of water, if I'm not mistaken. Yeah, 119 grams of water and 45.2 grams of solute. So 119 grams of water divided by 18 grams per mole gives us 6.611 moles. Now, knowing that 0.9474 over X plus 0.9474 equals 6.611 over 6.611 plus n of the unknown. We can solve for n of the unknown the same way we did the last guy. So we get the n of the unknown to be 0.36712 moles. Now, knowing the weight of 45.2 grams, and we divide it by our 0.36712 moles, we would get the molar weight of 123.12 grams over moles. Finally, number 33, the dissolution of 7.75 grams of substance in 825 grams of benzene at 298 raises the boiling point by 0.575 degrees Celsius. Note that the Kf equals 5.12 Kelvin per Kelvin kilogram per mole. Kb is 2.53 Kelvin kilogram per mole, and that the density of benzene is 876.6 kilograms per meter cubed. Calculate the freezing point depression, the ratio of vapor pressure above the solution to that of the pure solvent, and the osmotic pressure, and the molecular weight of the solute. Note that the P star of benzene is 103 torr and 298, so it's a little bit of a needs to be done into this one, but all in all, it's not that bad.
We are given all the following information, and we're asked for this problem, this last problem, 33. Find what is the delta TF of benzene, what is our osmotic pressure, a ratio of P over P star, and our molar mass of our solvent, given the fact that we know the grams of solute, the grams of benzene, the delta T boiling, the relative freezing point depression and boiling point elevation constants, the density of benzene, and the pure pressure of benzene. So, rid of that. So, with that in mind, we'll go ahead and get started. The first thing is to find out what is the molality, and that's going to be our starting point. Knowing that delta TB is going to be equal to KB times molality. So we can set that clearly 0.575 equals 2.53 molal times molality, because this is a non-ionizing. Dividing 5.75 by 2.53, you would get the molality, which is going to be true for all the situation, is 0.2273 molal, which is moles per kilogram of solvent. That's going to be important later. The first thing we could easily calculate is what is the freezing point depression. Well, the freezing point depression is just going to be delta TF is equal to negative KF times molality. So our KF is 5.12. Our molality is 0.2273. Wow. We multiply those across, and you would get freezing point depression would be negative 1.164 Kelvin. So we've seen a freezing point depression of negative 1 degrees Kelvin. And with that in mind, we can also find the molar mass relatively easily. But we have to turn molal into moles using the fact that it's kilograms of solvent. So we need to find how many kilograms of the kilograms of solvent. We said there was 825 grams of benzene. So our molal being 0.2273 moles per kilogram, and we multiply this by 0.825 kilograms, it would give us the moles of our solute. So 0.2273 times 0.825 would have approximately 0.1875, we'll say 225 moles. Finding our molar mass at this point is just a matter of taking the grams of solute, which was already given to us as 7.75 grams of solute, and dividing this by our moles of solute, 0.1875225 moles. And this will give us our molar mass. So 7.75 divided by 0.1875225, a molar mass of something like 41.3 grams per mole. That was relatively simple so far. Now comes a little bit trickier. If we want to, say, find the osmotic pressure. Osmotic pressure is pi RTC. We need to find the concentration. The temperature is at 298. So if we're going in bars, R is 0.8314 bar liter mole Kelvin. And we have temperature 298 Kelvin, but we need to know what is the concentration. That's one thing we don't know, but we do know the molality. So the brilliant thing is we've just figured out the moles. The mole concentration is moles of solute over liters of solution. Liters of solution. So we've been given the density of benzene. We're going to have to make some assumptions that the density of benzene doesn't really change with the added 7 grams of solute. So we're going to just essentially go, so 1875225 moles divided by, we said we have 825 grams of benzene, which is 0.825 kilograms. The density of benzene is something like 887 kilograms per meter cubed, and in 1 meter cubed there is 1,000 liters. So 0.825 kilograms divided by 0.887 kilograms per liter means we have a volume of 0.930 liters. I'll say 9301 liters. So So our concentration is divided that by 0.9301 liters. Concentration becomes 8725225 divided by 301. Concentration is something like 0.2016. We'll say 2. Now that's going to go up to there. So 0.20162 times 298 times 0.8314 gives us a osmotic pressure of something close to 49.95 bar. So pretty high. Wait. Oh, 8. So move the decimal 1. 4.995 bar. It's 0.08314. That's our R. Finally, what's our mole fraction? Our mole fraction is P. We want to find P over P star. Well, we've already kind of found our mole fraction. So what is a partial pressure? We want to know what is P if P star times X of benzene. Well, we need to find how many moles of benzene are in 725. In 825. Benzene is something like let's see. Benzene is 6 plus 6 is 78 grams per mole. And so at 825 grams, at 78 grams per mole, 825 divided by 78, something like 10.5769 moles. So the mole fraction would be something like 10.5769 over 10.5769 plus our original moles of 0.1875225. So 8.75225. Our mole fraction is something like, so that's our mole fraction. Our mole fraction is something like 0.9826. And so with our P star, working from left to right, P star of 103 times the 0.9826, our partial pressure of benzene, would be 101. So 101.2 would be our pressure of benzene. So that is taking a look at one fact about a solution and turning that into all the facts about that solution, step by step by step. Okay? And so that finishes up our chapter 9, at least the homework that I had previously assigned for my students. Have a good day.